Well, this is the third and the last one in this sequence of videos on eigenanalysis using R and using a toy data set. Now, we have basically finished whatever we wanted to say in the last video, but this video is for two reasons about R. So, these are some about technicalities of R. I'll be talking about one particular technicality that I used in the last video without really explaining. That is, when I said ij, then I wrote dollar val and dollar vectors. So what is the dollar thing? Well, when we use R, there are two basic data types that R supports. One is an array, that is numbers, that are like vectors and matrices or things like that, which all contain the same type of data. If one of them is an integer, everything is an integer. Everything else is also an integer. Or if one of them is a floating point number, everything else is floating point number. If one of them is a string, everything else is also a string. So that's called an array. And I can quickly show you examples of arrays are like C, 1, 2, 3, 4. So that's an array of integers. If I write C1, 2 and then a string, in that case everything becomes a string. So the first entry now becomes the string 1, not the number 1. So everything must be of the same type. Now in many situations we have to have a list of objects of different types, like C structures. Now for that, the particular construct that R has is a list. So if I write, say for example, TMP equal to list, I can put whatever I want. So I can say name equal to, say, Ram, and age equal to 56, and say I want to put these two things. In that case, it's a list of two things. One of them is a string and the other is one integer. You can now look up what is in TMP. So it will be name and age. Now notice the dollars. So dollar name means it is the name field of the variable called TMP. So you can access that later by typing TMP dollar name. So this is what is done using the dot operator in C. So that is Ram, and you can call age, and that is 56. You can also abbreviate it. That will also work as long as the abbreviation remains unique. If it becomes ambiguous, then R gets confused and reports null. So let's quickly see an example of that. Earlier I had got age, and it had got two components. One is values and the vectors. So when it is values and vectors, then both of them start with V. So if I just abbreviate it to val, it was okay. If I abbreviate to VA, that is also okay. But if I abbreviate it to V, because it clashes with both vector as well as values, it just says null. Pretty bad thing, because it should ideally say more than one field matches, so I cannot produce output. And in fact, if you just type some garbage name which is not there, even then it produces null. So programmatically it becomes a little bit tricky to figure out whether you have just given the wrong name or the right name, but which is ambiguous. Anyway, so this is the way by which functions in R return multiple objects, because the way R is created, each function can return only a single object. So if you need to return multiple objects, you have to bundle everything in a list and return that single list object. Lists are very general. List may contain anything, even other lists. So here is another example. So I can have, again, the temp example. Temp is list this, and then I can put another one. Say I can put X equal to a list which is again of various things like A equal to 34, B equal to RT. So now TMP is a big thing. So TMP has got age, it has name, age and X. Inside X I have got A and I have got B. So I can refer to these things as TMP $X $B. So B inside X, which is inside TMP. Now it is possible to refer to these things using indexing. So I can refer to this TMP 2 square brackets then 1. So that means the first one name. Then if I write this, then I will get the second thing 56. So in this way, if I want to loop through it, loop through all the fields of a list, I can do so. Okay, now let's quickly see how to carry out this eigenanalysis or principal component analysis using R without explicitly computing the eigen decomposition. Because it is such a very popular method, it is only natural that R already has some built-in support for it, and indeed it has. There are two different functions, one is called prcomp and the other is called princomp for carrying out principal component analysis. Now prcomp is the one that is more modern and the one that you should use. It uses SVD, whereas princomp actually does spectral decomposition and proceeds like that. So prcomp is able to handle bigger data sets because it really does not explicitly compute the covariance matrix. It uses singular value decomposition in a clever way. So let me quickly show our case. So I already had the data set, my data from the last video. So all that I have to do is to run this and collect the output in a variable which I call val. Well, it has finished. Now, like most functions in R, this also returns a list. So list of various objects. I need to know what are the objects that are stored inside the packet called val. Now a simple way to figure that out could be to just look up the help of prcomp and then you will see principal component analysis, descriptions, usage, arguments. You do not need these things right now. What you need are not the details but the value. It says it will return a list of class this containing the following components. SDEV, the various standard deviations of the principal components, that is the amount of spread. Rotation, that is the rotation matrix, that orthogonal matrix, and then then X, then center and scale and things like that. So that is one way by which you can figure that out, and the details are all given here. But in case you are just interested in the names, then you can type names of val and it will give you the list of all the names. So whenever you have a list and you want to know about all the components in it, just use names of that list. So SDEV, rotation, center, scale, X. So SDEV, as I already said, SDEV are basically the square roots of the eigenvalues that we had obtained earlier. In case you are not sure, let me just try. I had the values, eigenvalues, and you see they are exactly the same thing. Rotation are nothing but the eigenvectors because that's a rotation matrix. Now, of course, you get all these things here. Now, I will show you something which is plot. Plot of val will produce what is commonly called a scree plot. A scree plot. So let me just type the word scree plot. So scree means all the boulders etc. that accumulate at the foot of a hill, the things that roll down, and someone thought that this plot looks like those boulders. Now these are nothing but the various eigenvalues. So this is the largest eigenvalue, the heights represent the eigenvalues, the widths are just of no importance, it's a bar chart. And then the next eigenvalue, the third eigenvalue, and I can see that this one is very big, this one is also has some considerable size, but this one, the very last one, is essentially 0. This is what tells me that the data set has spread in one direction, a little bit of spread in another direction, but that's it. There's hardly any spread in the direction perpendicular to that. So effectively, this is a two-dimensional data set. So the scree plot immediately tells you what is the intrinsic dimension of the data set. Just count the number of eigenvalues of appreciable size. Appreciable you decide by just visual inspection. So you really do not need to carry out eigenanalysis and find the eigenvectors yourself. You can just use, and you should just use, the peer comp function, and that will do everything for you.